Yes, sir.
Yes,
Yes,
sir.
sir.
All your blessings, sir.
No, no, no. It's all your research work.
No, sir. It is just because all of your blessings and whatever you have taught me, this is all
No,
because
no,
of
no.
that.
Come on. These are all your hard work and talent.
Thank you. Thank you so much, sir.
Your
So,
research work.
yeah.
No, sir. It is just because all of your blessings and whatever you have taught, this is all
No,
because
no,
of
no.
that.
Come on.
So
These are all
it's on
your
record,
work
and uh, we'll uh, we will now start. Means already.
Whatever you have taught, this is all
No,
because
no,
of
no.
that.
Come on.
Okay, so we wish to start the formal part of the lecture, and it's now on record also. Uh, so uh, so I request everybody other than Professor Patrick to mute, and it's now on record also. So I request everybody other than Professor Patrick to mute, and now on record also. So with permission of everyone and especially Professor Ghatak, I would like to start today's event. Uh, And the background is the event is that recently we have lost a very distinguished fellow of the National Academy of Science, Professor Narlikar, who was long associated with the National Academy of Sciences. He became fellow of the Academy at 1988, and at different capacity, he helped NASI and for last 37 years. And the best thing is that NASI's one of the mandate is to bring science to society. So we call it science and society. And probably J.V. Narlikar was one of the biggest example to how to bring science to society. He popularized science. There were so many people become interested to science specifically, and more particularly to astrophysics because of his books, his lectures, and there are many examples. So he visited JIT, who is what is a co-organizer of this event in 2009, end of 2009, and our auditorium was new and it was fully packed. And immediately after that, we received several requests to open an elective on astrophysics. So I started teaching a popular course on astrophysics, and that still it is running. And that course started because of the uh, presence of Professor Narlikar in 2009 in our campus. So it's just an example. He must have inspired many such people, and eventually many of our engineering students shifted and they are doing good astrophysics. So one of them is with Pratika Dal, who is now a professor of astrophysics, and she she was well, there are many students who become interested because of Professor Nallikar's lecture. Then after Professor Narlikar passed away, we thought that we'll organize a memorial lecture or a special lecture to discuss his contribution as well as to talk about his life. And we could not think of anybody better than Professor Patrick Dasgupta, who heredited many things from Professor Narlikar. He was not only his PhD student, uh, he heredited that skill of popularizing science and popularizing physics to reach mass, and his talks are always mesmerizing. So Professor Patrick Dasgupta was with Delhi University, and he has taught generation of students at DU directly, and many of our students and ourselves also indirectly through many workshops, conferences, and such things. And before that, he did PhD with Professor Narlikar, and even before that, he was in BITS Pilani doing his bachelor's and master's. So, without further delay, with an expectation that today's lecture will add up to his indirect students, few new students will also join in the great big list of Patrick's direct and indirect students. And without any further delay, I request Professor Patrick to share his slides and speak about life and work of Professor Narlikar. So over to you, Professor.
Thank you very much, Professor Anirban Pathak. First of all, I thank Professor Ghatak, Professor Anirban Pathak, and Professor Papia Chaudhary for organizing this lecture. So I'll start sharing the slides.
So it's allowed, please share.
So I'm not seeing the
Slide sharing button.
yeah. Are you able to see the slides?
Yes, but it's not in full screen mode.
I've shared. Yeah, I'll do that. Are you able to see the full screen?
It's loading. And now it's proper.
All right.
So you can start.
Very good. Oh, fantastic. Yeah, great. So today I am going to speak on the incredible voyage of Professor Jayant Narlikar, who essentially straddled both the microcosm and the macrocosm. And here is Professor Narlikar talking about the difference between the Big Bang model and the steady state model, where the scale of the universe as a function of time has been shown. Professor Narlikar would call the scale of the universe to be S. I, in my lectures, would call it A of t. And as you can see that on the blackboard, you have where the Ricci tensor is proportional to the energy momentum tensor plus a question mark, because this question mark, Professor Hoyle and Narlikar filled it with the creation field. We'll come to that soon. And here is a picture of Professor Narlikar with his mathematician wife, late Professor Mangala Narlikar, whom we lost last year, unfortunately. Right. So I'm not going to give the details of the various prizes that Professor Narlikar received right from 1962 onwards. Primarily, you can see that Kalinga Prize in 1996 and the Padma Vibhushan in 2004, that sort of are the accolades that anyone could be cherishing. Right. So now, Professor Narlikar, it's amazing that the kind of academic work, the plethora of academic work, from the gamuts of action at a distance to black holes to quasars to microwave background, and then to writing books, popular science articles, science fiction, novel, and stories, and creating Ayuka. So it's incredible that a single individual could accomplish all these. And that's the reason I have called this lecture his multiverse odyssey, because he really sailed across a multiple of universes. Professor Narlikar, when he was a young adolescent growing up in the campuses of BHU, where his generalist and distinguished father was a senior faculty member and for a while the vice chancellor, he acquired the taste and the passion for solving mathematical puzzles. His uncle would every day before going for his work on a small blackboard placed in their house would write a mathematical puzzle and leave for his work. Then young Jayan would stare at the blackboard and start solving the mathematical puzzle. And that's how, right from the beginning, a quantitative reasoning and a passion for mathematical work started in the young mind of Professor Jayant Narlikar. Eventually, after when he was ripe for a research journey, he went over to the Cambridge University, United Kingdoms, where he met the great physicist Sir Fred Hoyle. So Professor Jayant Narlikar, very much like his PhD supervisor Fred Hoyle, they sort of acquired a philosophical outlook in which they believed that even the world of microcosm inhabited by elementary particles, at some level, their properties are determined by the presence of matter in the universe. And because you are talking about matter in the universe, clearly this comes under the purview of the field cosmology. And because one is saying that properties of the microcosm are determined by matter in the universe, one naturally is moving towards the Mach principle. We'll talk about this as I proceed. So, in other words, right from a young age, Professor Narlikar embarked on a journey into the field of cosmology, general relativity of space-time, and Mach's principle. We all know that cosmology is a field which deals with the physics of the origin, composition, and the evolution of the large-scale space-time geometry with the matter in it and its distribution of matter. Now, in 1929, after Hubble had discovered that galaxies are moving away from each other, the Big Bang model to describe the universe had gained a lot of popularity. Even before the real discovery, Friedman and independently George Lemaitre, they had already worked out the theoretical formalism in which they showed that if matter in the universe was distributed in a homogeneous and isotropic fashion, then the geometry of the space-time would either expand or contract. In fact, George Lemaitre had the premonition that we live in an expanding universe. This is all in 1922 and 23, 6 years before Hubble discovered that the redshift of galaxies are proportional to distance, and thereby the galaxies are moving away from each other. So, Big Bang model gained popularity, and physicists like George Gamow, Edward Teller, they embraced Big Bang model and started working out various aspects like their influence on nuclear fusion to cook heavier elements starting from hydrogen and so on. The Big Bang model, or rather, whenever the matter is distributed homogeneously and isotropically, there is only one function of time which describes how the universe is expanding. It's called the scale factor A of t. In the picture of Professor Jayant Narlikar, he calls it S of t. The Hubble parameter is related to the time derivative of the scale factor. Hubble parameter is simply dA by dt divided by A of t. And today's Hubble parameter the present epoch Hubble parameter, which is also called the Hubble constant, is this object evaluated at time t naught. While general relativity tells us that cosmological stretching of various wavelengths, so Z is given by divided by the scale factor. The minus one has gone out of the slide. So the correct expression is A of t naught divided by A of t minus 1. That is the redshift of an object whose light was emitted at time t and is being received today at time t naught. So the Big Bang model would say that universe began when A of t was 0 at t equals 0, and A of t continuously expanded and the distance between objects kept on increasing. In other words, earlier on, the elementary particles, the density and the volume scaled as cube of A of t, and thereby the density keeps on decreasing. And when the matter like quark, gluon, plasma, the soup of neutrinos, electrons, positrons, photons, etc., they cooled, they gave rise to various phenomena like formation of neutrons and protons, then formation of helium and other light elements, then eventually formation of galaxies. And after tennis for about 10 years, even planets were formed, and there we are, thinking individuals created out of all these quantum mechanical entity, and we who are made of these quantum mechanical entities like ultimate theories like quantum theory and general relativity. That is one of the biggest philosophical puzzles. Now, I mentioned that Professor Narlikar and Professor Fred Hoyle, they believe that Mach's principle played a very important role in the world of the microcosm. Now, what is Mach's principle? Mach's principle, as Mach himself, when he read about the Newton's famous bucket experiment, when Newton showed that if you fill a bucket with water and spin the bucket, initially the water would not rotate and the surface of the water level would be flat. But as the frictional forces would transmit the rotation of the bucket to the water, so in other words, the relative acceleration between water and the bucket did not make the surface of the water concave, but only when the frictional forces transmitted the angular speed to the water, when the relative acceleration between water and the bucket became zero, only then the water surface became concave because of the pseudo forces, fictitious forces, because now it is in a non-inertial frame. So Newton argued that acceleration is an absolute quantity, and acceleration with respect to an inertial frame is something that leads to fictitious forces. In other words, Newton argued that inertial frames are those frames where there are no fictitious forces. Fictitious forces are those forces which do not originate from any matter. They just are resulting because of the frame being not inertial. Mach, on the other hand, he realized that this is something very surprising, because according to Mach, everything is relative, including acceleration. Mach conjectured that had Newton's bucket been larger, as massive as the rest of the universe, then even in the beginning, when the bucket was spinning and the water was at rest, there would have been a concave surface of water because of the fictitious force. Mach, in fact, claimed that inertial frames are those frames of references which are either at rest or uniformly moving with respect to the distant stars. And now we say the distant galaxies. Now, Mach had a very big influence on Albert Einstein. In fact, Albert Einstein, when he was developing his general theory of relativity, which is a relativistic theory of gravity, he uh, had in mind that he would be able to explain Mach's principle. But I'll tell you a little later what actually he discovered. Now, Hoyle and Narlikar from 1964 to 2003, they sort of took Mach's principle by sort of adopting that inertial masses of particles of all matter are generated by interaction with other particles. That means the distant matter, they are also composed of particles. It is their interaction with each other that generate the inertial masses. And through direct action, I'll talk about direct action soon in other slides. On the other hand, there was another earlier version of Mach's principle being incorporated in the theory of gravity. This is by Brans and the versatile physicist DT. They proposed in 1961 that Mach's principle can be incorporated by saying Newton's gravitational constant is generated by the presence of other matter in the universe. That is, there is a scalar field which is sourced by all matter in the universe, and inverse of the average scalar field is what is gravitational constant. And in fact, it is gravity which tells us what the masses are, because it is the gravitational constant which can be used to determine the Planck mass. So these are two different ways of incorporating Mach's principle in a theory of gravity. But of course, today we know that all experiments suggest that Einstein, his general relativity has been quite successful, where in Einstein's theory, capital G is a constant. It is similarly, masses are not generated by anything else. Right. So now what is the distant matter like? If you take a powerful telescope and look at the universe, you will find that the universe is filled with galaxies. There are elliptical galaxies, there are spiral galaxies, and so on. Even at a much larger scale, you can see each bright dot is a galaxy in this. You can see how homogeneous and isotropic the distribution of galaxies are. Of course, at certain scales, there are overdensity like these filaments and shells, etc. But on scales of few hundred million light years, the universe is homogeneous and isotropic. And that's the reason why a universe, a isotropic and homogeneous model for the universe is a good model. Now, galaxies, there are the spiral galaxies. So spiral galaxy, if you view edge on, it will be like a disk galaxy. But then there are bigger galaxies. These are elliptical galaxies. These are much bigger than the spiral galaxies. Here is the elliptical galaxy M87. From the core, you can see a jet coming out. We'll talk about these later on. And the M87 has a huge supermassive black hole weighing 6.5 billion times the sun's mass. Here is another elliptical galaxy called sombrero galaxies because of the sombrero hat-like structure. So it is believed that elliptical galaxies are formed by the merger of two or more spiral galaxies, because elliptical galaxies don't seem to have much angular momentum, while spiral galaxies have angular momentum. And if two or more spiral galaxies with their angular momentum vector in different direction, when they merge, the net angular momentum will be small. And this is the theory which currently is favored as to how elliptical galaxies are formed. Here is interacting galaxies which merge, and these are actual observations, which merge and possibly give rise to elliptical galaxies. here are more interacting galaxies. Now, Hubble discovered that distant galaxies from the emission lines, the emissions lines are shifted towards the red. Hubble shift. He interpreted that the Doppler shift V by C Z, according to him, the redshift Z V by C, he found is equal to the Hubble constant h0 times distance. Today we know that actually the galaxies are not moving. Rather, it is the geometry, the space-time geometry is expanding. This is because of Einstein general, in which rather gravity is, and energy and momentum of matter, it curves up the space-time geometry. And if you have, as Friedman and George Lemaitre had shown, then the space-time geometry is such that either you will have the universe to be expanding or contracting depending on the scale factor A of t, whether it is increasing with time or whether contracting with time. So in other words, the Big Bang model says that A of t increases with time, and people like Gamow, Taylor, Alpher, Harman, they showed that as the universe cools, then various elements, light elements, starting with hydrogen, can be synthesized, like helium, deuterium, lithium, etc. And the scale factor, here's a picture showing how the scale factor changes with time. In the vertical, a closed universe and then again collapse. So it starts with A equals 0, and there's a big crunch, again A equals 0. While decelerating universe, the scale factor keeps on increasing, but the expanding universe, they never collapse back. While today we know that all observations tell us that we inhabit an accelerating universe where the scale factor is not only increasing in time, but the rate at which scale factor is changing, that itself is increasing with time. So it's interesting that steady state model, which was championed by Thomas Gold, Herman Bondi, and Fred Hoyle, they in fact talked about a scale factor which is exponentially increasing with time. For them, scale factor increased as e raised to power some constant, which they called it h times t. All right. However, steady state model is very different from Big Bang model, although the geometrical element is described by the same Robertson-Walker line element. Here is a picture of Thomas Gold, Herman Bondi, and Fred Hoyle, who Gold and Bondi in 1948 published a paper on steady state model, and Hoyle independently in the same year also published the steady state model. You might ask, what was the motivation? The motivation was that in 1948, the Hubble parameter, the Hubble constant, that is Hubble parameter today, was measured erroneously, and its value was very high, 600 kilometers per second per megaparsec. And this would mean that the age of the universe will be billion years old. Why? Because in the Big Bang model, the age of the universe is proportional to 1 over h0. Now, if the age of the universe is 1 billion years, that contradicts the fact that Earth's age is more than billion years. How can Earth be younger than universe? And that is the reason why these three great physicists proposed the steady state model, in which the universe did not have a beginning, doesn't have an end. It keeps on expanding exponentially, but the universe looks all the time same. That is, the universe in spatial symmetry not only is invariant under spatial translation and rotation, but under time translation also, the universe on large scale is invariant. So there was a bigger beauty, there was an aesthetic a beauty that steady state model not only has symmetry under space translation, rotation, as well as time translation. You might say that universe, if it is exponentially expanding, how can the density remain same? So here is the picture. In the steady state model, the universe is exponentially expanding, but the density of matter still remains same. On the other hand, in Big Bang cosmology, it is expanding, but the matter density is decreasing, which is seen by the distance between galaxies increasing as the universe expands. In steady state model, they argued that yes, the universe is exponentially expanding, but matter is being created homogeneously and isotropically in between spontaneously at a very small rate, one atom per megaparsec cube volume. 1 megaparsec is 1 million parsec. 1 parsec is about 3.2 light years. These are the distance scales. So, in other words, that steady state model said the universe is accelerating, and they, Hoyle and Narlikar, they propose a field called creation field, shortened to C field. Hoyle had already, in a steady state model paper, 1948, had talked about such a field. But when Jayant Narlikar joined him as a PhD student, they did elaborate mathematical calculations and published 7 or 8 papers on the dynamics of the C field. Now, it is very interesting that today, as I said, that the observations suggest that the universe is not only expanding, but the expansion rate is increasing with time. That means we inhabit an accelerating universe. And one of the ways to explain accelerating universe is by proposing something called phantom field. There are other ways, quintessence and other fields, but phantom field is very much like C field. So it was really prescient of Hoyle to think of a field which modern day cosmologists have used it, of course, calling it phantom field, but in the framework of Big Bang model, not in the steady state model framework. And then, so here is a page of one of the later papers where the dynamics of the C field, the C of X, this is a scalar field, and the dynamics of the scalar field is given. And this is the direct action theory, that means incorporating Mach's principle, where masses are generated through direct interaction with other particles. Let me not go into the mathematics. And then from 1993 to 2003, they worked out a modified version of steady state model called quasi-steady state model, where overall the universe scale factor, remember that Narlikar and his collaborator, they use S of t as the scale factor, while I'll be calling it A of t. Overall, the scale factor increases exponentially as in steady state model, but over that there are oscillations. And these oscillations, because of the oscillation, if you are in a increasing phase, it would look like a Big Bang model. All right. So locally, it would look like a Big Bang model when it is increasing. But then when it is decreasing, it would be like a Big Bang collapsing model. So both features of Big Bang and steady state have been incorporated in the quasi-state model. These were the interests of Professor Narlikar from 1993 to 2003. And one of the predictions of quasi-state model was that when the universe is in the contracting phase, you will see quasars which have blue shift instead of only having red shifts. So in other words, that the quasi-state theory relies on small mini banks resulting from the creation fields. Whenever there'll be a mini bank, it will expand and again recollapse. Again, another mini bank creation field expansion collapse. Such mini banks would give rise to generation of gravitational waves, because whenever matter distribution changes anisotropically, gravitational waves are created, and in principle you can also constrain the energy density of such gravitational waves using pulsar timing array. So Professor Narlikar and I, we worked out and published a paper where we gave the details of gravitational wave produced from such mini banks and how one could constrain them by pulsar timing array. Now, I talked about direct action, where Hoyle and Narlikar used direct action theory to interpret Mach's principle. What complete opposite, namely the field. As we all know, Faraday, he was the first to talk about that there are fields which essentially lead to forces. So Faraday, of course, was motivated when he put a bar magnet into a distribution of iron filings, and he saw these patterns of iron filings, and therefore he claimed that the iron filings are oriented along magnetic field lines, and when you bring two bar magnets, north pole facing, the iron filings would show up this way, and you can see the field lines give you the repelling each other. So Faraday, due to fields being produced by either electric charges or magnets, and the fields, and when a charged particle or other tiny magnet come, they don't directly interact with the original source, but they interact with the fields themselves. So this was the field theory concept, which was the earliest proponent was Faraday, and it was very successful. After all, the entire Maxwell's electrodynamics came from field theory. The fact that when the fields get disturbed, they propagate as waves. They were the Hertz experiment showed the electromagnetic waves and so on. On the other hand, the direct action is theory, action at a distance theories are theories in which there are no force fields at all. So particles directly interact with each other without being mediated by any gauge fields like photons, gravitons, gluons, or W bosons, etc. They directly interact with each other. Of course, Lorentz invariance is maintained in the sense that if a particle moves at one point, the action is delayed by proper speed of light and is communicated with another particle. So Lorentz invariance is maintained, and action at a distance theory for electrodynamics was worked out by Wheeler and Feynman in 1948 and 1949. Hoyle and Narlikar, realizing that they can use this theory to sort of modify Mach's principle, incorporate it, and have a general theory of relativity version of it. So they incorporated the direct at a distance formalism of Wheeler and Feynman from 1964 to 1972. They worked out a series of papers, and here are the prints of those papers. As you can see, in the direct action, if you have two charged particles, EA and EB, they interact, and there is this Dirac delta function whose argument is square of the SAB, which is C squared T minus T1 squared minus X1 squared minus, and so on. It's the relativistic delay. So there's a relativistic delay incorporated already, and each particle is seeing each other. That was the original paper of Wheeler and Feynman. What Hoyle and Narlikar did was they said that even masses are generated by the direct action through a propagator, bipropagator G, and masses are generated by particles seeing each other. And similarly, of course, the electric charge, of course, interacted through this, and they worked out a full formalism to give the theory for the direct action of both electrodynamics as well as gravity. Later on, the quantum electrodynamics was also reformulated in action at a distance formalism. This was in 1969 and 1971. And basically, Hoyle and Narlikar used Feynman's path integral formulation of quantum theory to cast the direct action classical theory into quantum electrodynamics. We all know that in classical mechanics, a particle moves from one point to another, the actual trajectory extremizes the classical action. The action is given by time integral of Lagrangian over dt. On the other hand, Feynman, uh, he discovered that entire Schrodinger quantum mechanics, Schrodinger-Heisenberg quantum mechanics can be formulated using path integral, where the probability amplitude to go from one point to another point, the probability amplitude to go from one to another point is given by summing over e raised power I action divided by h bar. H bar is Planck's constant divided by 2 pi. So take e raised power I action divided by h bar, and s, the action, of course, is a functional of path. And therefore, if you choose a different path, the value of the action will be different. So what Feynman did was he showed that the probability amplitude to arrive at the final point starting from the initial point is given by all paths that connect the initial point to other point. You sum over this quantity e raised to power is by h bar. Note that in quantum mechanics, iota, that is square root of -1, has to appear, and h bar, the Planck's constant divided by 2 pi, also has to appear. But in Feynman's formulation, even the classical action appears. That was a very interesting formulation, because in Feynman's formalism, if you know the classical action for any theory, you can quantize it by using the sum over all paths of e raised to power s by h bar. Now, of course, sum over all paths is a very complicated sort of measure of integral. And for a long time, mathematicians wondered what kind of a measure is one talking about when you are talking about sum over all paths. But interesting thing is the results come out very nicely, consistent. Right. Now we talk about Narlikar's work in black holes and white holes. So Narlikar, he also looked at the black holes. As you know, Carl Schwarzschild in 1915 itself obtained an exact solution from Einstein's general relativistic equation. And in particular, if a spherical mass, if its size shrinks to a radius less than 2 gm by c square, then there appears an event horizon such that light from within the event horizon cannot escape out. And that today we call as black hole. And the event horizon radius is called the Schwarzschild radius. And in numerical number, the Schwarzschild radius of any object, spherically symmetric object of mass m, is 3 kilometers time mass divided by sun's mass. All right. Let me not go into the mathematical details about the line element of Schwarzschild metric. And let me also skip this slide. So essentially, what Narlikar with his PhD student Rajiv Dhurandhar, they did lot around Schwarzschild black hole, around Kerr black tachyons created by Sudarshan and Mishra, where they made it that the mass of a particle, which is rest mass divided by square root of 1 minus v square by c square, if v greater than c becomes imaginary. That's why it can exceed speed of light. But Sudarshan made this m is rest mass divided by square root of 1 minus v square by c square. What if the rest mass itself is imaginary? Then c, then the move that's how tachyons as a proposed particle was born, which have to always move with speed greater than c. Unfortunately, no one has observed tachyons, but Narlikar and Sanjeev Dhurandhar, they worked out a series of papers of the dynamics of tachyons in both Schwarzschild black hole as well as rotating black hole called Kerr black hole. We all know that black holes, there is great indirect evidence for black holes because we have our emission at the rate of 10 can be produced. The theoretical models say that if you have a black hole, matter accrete up to the event horizon. And that's how, since you go close to the event horizon, the entire gravitational potential energy can be mined. That's how the quasars, radio galaxies, they are so luminous. And the indirect evidence of a supermassive black hole at the center of our galaxy, Milky Way galaxy, was given by monitoring the motion of stars in real time around this center of the Milky Way, denoted by this asterisk, the star. And for this, and we also know the central region of our galaxy called Sagittarius A star, that is also very luminous. It emits a lot of X-rays. And of course, we know that the mass of the supermassive black hole here is about 4 to 5 million times heavier than the sun's mass. And because of these observations and because of the pioneering work of Penrose and Hawking, who used the Raychaudhuri equation to prove that matter, when they collapse, necessarily under certain condition have to form black holes, these three individuals were awarded the 2020 Nobel Prize in Physics. Now, what Professor Narlikar did was he also used one of the ideas that come from time symmetry of general relativity. General relativity is time reversal symmetric. And that's the reason why you can say, well, when matter is collapsing, here matter is collapsing and finally all matter collapses to a point. So this is your black hole. This point is a singular point because there the curvature radius is 0. But of course, it is covered by an event horizon. But what about the time reverse picture of it? Time reverse picture will be from the singularity, matter is coming out. Time reverse version of black hole is called white hole. Of course, later people like Thorne, etc., showed that yes, white holes mathematically are allowed, but they are very unstable. A little disturbance, a white hole will immediately again collapse into a black hole. So, in other words, the whenever classical general relativity would say that if you have a black hole, possibly that the entire matter goes through a narrow neck called the wormhole and emerges somewhere else as white hole. So, J.V. Narlikar and K.M.V. Apparao, both from TIFR, they gave a very innovative suggestion that white holes probably can explain very bright X-ray and gamma ray burst sources. As you know, the American spy satellite, Vela satellite, had instead of seeing the nuclear activities from Soviet Russia, they had detected serendipitously gamma ray bursts lasting for a few seconds to thousands of seconds. And these turned out to be bizarre objects. Today we call them gamma ray bursts. And they were reported by the uh, physicists working for the Vela satellite around mid 70s. And in 1974, probably reported around 73. And in 1974, Narlikar and Apparao, they sort of propounded that sudden burst of matter coming out of is the long duration gamma ray burst is when a massive star, a star whose mass is 30 to 40 times more than sun's mass, when the core collapses, the core turns into a 10 to 20 solar mass black hole, and there's a disk around it, and it's the disk for a short while when it is going around the black hole produces the gamma ray burst. Suddenly produces prompt gamma rays, and that's what we see as gamma ray bursts. But the thing to note is Hoyle and Narlikar, they always use their creativity to always think of new models, which goes against the grain of models which are being propounded by others. Then we come to radio galaxies and quasars. As I had mentioned, that there are these powerful radio jets coming from elliptical galaxies, and the jets go much further away. I mean, they can go up to few million light years, while the galaxy size maybe would be of the size will be 300,000 or rather 1,000 light years or 3,000 light years, while the jets can reach up to million light years. What causes such collimated jets? Here is a picture of the core of this galaxy, and you can see that right at the center there is a bright object, and this bright object is believed to be the bright accretion disk around a supermassive black hole. Okay, so the M87 galaxy that we saw earlier with a jet, there the core is also, you can see, a bright object, and probably this is the accretion disk around the black hole. Now, Narlikar and P.K. Das, as I said, they always wanted to explore new ways of looking at it. They said that the quasars, here is a quasar. Quasar observationally appears like a star, although it's very far away and incredibly luminous. They pour out 10 to the 49 ergs every second, if you believe that they are far away. Now, Narlikar and P.K. Das from 1975 to 1976, they worked out a theory in which quasars are not very far away. Rather, they are smaller globular size, cluster size objects ejected from the centers of galaxies. But you might say that how can they be ejected with relativistic speed? After all, they are as massive as 10 to the power 6 times mass of the sun. Well, Narlikar invoked Mach principle. He said that all masses are generated by interaction with other particles. If something is created today, its mass will be zero because it hasn't had time to interact with other particles. And that's why when it is ejected, its mass is zero, and it can be ejected with 0.99 C, etc. And therefore, the ejection would lead to Doppler shift, and high redshift is due to Doppler shift. But then immediately critics of this theory asked, but we should see also blue shifts. If a quasar is ejected towards us, instead of redshift, high redshift, we should see high blue shift. And for that, Narlikar, with another graduate student of his, Kandaswamy Subramanian, they worked out a way where this ejected object, when it is ejected in the forward direction, because of the bow shock, it it acquires a very thick mass, and you will not see any radiation in this direction. But because it is being ejected with great velocity in the backward direction, if there is a small emitting region, it would form a funnels through which radiation can escape. So only if you are behind, you will see the radiation, and because it is being ejected with great speed, you will see Doppler redshift. But today, of course, we know that the consensus is that quasars and radio galaxies and blazars, they are because matter is churning around a supermassive black hole, and it is the gravitational potential energy which is being slowly lost as matter from far distance reaches the event horizon, and thereby huge amount of gravitational potential energy. It becomes gravitational potential energy becomes negative, more and more negative. But energy has to be conserved. Rest of its energy is being radiated out, as seen in radio galaxies, blazars, and quasars. All right. Now, I will talk about uh, Narlikar and his student Narayan Chandra Rana, late Narayan Chandra Rana, one of a very creative physicist. They're giving a very different model to explain the black body curve that was seen for the cosmic microwave background radiation. It's a fascinating story that two engineers, Penzias and Wilson, when they were building a very sensitive microwave antenna, they accidentally discovered the microwave background radiation, and cosmologists soon saw that it was already predicted by George Gamow, Alpher, and Harman in their Big Bang model. What they said was, when the universe started with Big Bang, it was very hot, and when it is expanding, it is cooling. At one point, when the protons would acquire the electron and form neutral hydrogen atom, because it is neutral, it will no longer interact that strongly with radiation. The radiation, because it's a thermal bath, the radiation which has a black body spectrum now will not see effectively the hydrogen atoms. They will escape like black body photons. And because the universe is expanding, the temperature of those photons, which were earlier about 1000 degree Kelvin, by the time universe has cooled down to present time, it will be observed as a black body spectrum at temperature 2.725 degree Kelvin. And this was noticed by many CMB probes like Kobe telescope, WMAP, and Planck telescope. And this was one of the reasons why Big Bang model got a feather in the cap, because it was predicted and it was seen. But Hoyle had pointed out a remarkable coincidence. He figured out that the energy density of the cosmic micro background radiation is very similar to the background stellar light energy density in our galaxy. So he thought, what if the cosmic micro background radiation is not cosmological, but it is a stellar light which interact with the interstellar grains like graphite grains and all, and get reprocessed and is emitted in microwave region. Then later on, Hoyle, Narlikar, late Narayan Chandra Rana, Sri Lankan cosmologist Vikramasinghe, they carried out elaborate research studies from 1968, 96. Iron they can sort of absorb supernova, etc., and will be processed and re-radiated in microwave background radiation. But today we know that such a theory is untenable, because the cosmic microwave background radiation, with whether it's a probe or WMAP or Planck probe, it has seen a dipole anisotropy. That is, the galaxy is moving towards the local supercluster. In that direction, the temperature of the micro background is marginally higher than opposite direction. And that means the difference in the temperature divided by temperature is 10⁻³ . It is tiny, but it has been detected. And one sees that the direction is the same as the direction in which the Milky Way is moving, and the motion is about 600 kilometers per second. Now, clearly, the stellar light processing being processed by interstellar grains and being radiated, that will not produce such a huge Doppler velocity. And furthermore, there is delta t by t being 10 to the minus 6, such uh, 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 fluctuations seen WMAP and Planck, and they presence of structures in the universe like galaxies, clusters of galaxies, and superclusters. So, in other words, Big Bang model is still the favored model as far as the cosmological dynamics of universe is concerned. The last thing that I'll talk about is Vikramasinghe and Narlikar, Tokoro, and Hoyle. They are claiming that life originated not on Earth, but they were deposited from objects like comets, etc. Because the main thing, as Hoyle had pointed out, is 14 billion years, as Big Bang would say, the age of the universe is not enough to create such a variety of living system, because you need mutations of chromosomes to create such variety. And Fred Hoyle, because he always championed steady state model, and steady state model because it doesn't have a beginning or an end, there is an eternity to create living forms. So therefore, Hoyle and his students, they championed the idea that life was created in the water ice of comets and are deposited on Earth, because comets keep getting, they bombard our Earth time to time. So basically, their theory was that from interstellar clouds, water was formed in planets and comets, and the so-called the uh, amino acids and other organic compounds, they in the comets they get synthesized to form complex proteins and DNA, RNA to give rise to living form. As I had mentioned right in the beginning, Professor Narlikar was a prolific science fiction novel as well as story author. For example, The Return of Baman is one of the very celebrated novels where you can see the inspiration of Harappan undeciphered scripts, but turned into a science fictionist ideas. Similarly, his novels on time machine. He has written many science fiction stories as well as novels. I think, how am I doing with time? Please let me know how much time. I would rather take questions than go further ahead. Anirban,
I was muted, so I was
how much?
making myself unmute. So it's about 10
Yeah, yeah.
minutes. You can speak and then we can take 10 minutes questions.
Oh, fantastic. Right. So let me go back to the quasars, because because P.K. Das and Narlikar, they talked about quasars being actually flung from nearby galaxies. So therefore, the redshifts are not cosmological redshift. A some time ago, people working on quasar redshifts had found that the redshifts are quantized in units of 72 kilometers per second times speed of light. That is, V by C was uh, V was 72 kilometers per second. That was the quantum. That means the gap between redshift had this kind of a value. And immediately, Hoyle, Burbidge, Narlikar, they sort of pounced on that observation, and they talked about quantum quantized redshift of stars, and they published two of the works on quasar galaxy association, that quasars are essentially not cosmological, but there's a bridge connecting them, their host galaxy, and similarly quantized redshift. I played in the paper, and the quantized redshift work was the last PhD student of Professor Narlikar, Devi Prasad, was essentially Devi Prasad Dwari, Narlikar, and my work. And we showed by looking at a large sample of quasars, redshift quantization, and the delta Z, the quantum is about 0.056. Now, the question is whether it is due to the error in measurement of redshift that you get when you do a power spectrum analysis, whether you get a spurious peak in the power spectrum, and thereby we infer that's a quantization, or whether it is something genuine, that only later analysis will tell. But all I want to emphasize is both Professor Hoyle and Professor Narlikar, they always believe that which are different from the mainstream theories, because the mainstream theories must be challenged by rival theories. After all, that was the spirit of science, because ultimately the arbiter of the correct theories are experiments and observations. But to be fair, I must point out that although the Hoyle-Narlikar theories were very beautiful, ground on the perfect cosmological principle and Mach's principle, uh, aesthetically there was beauty, but all observations today suggest that the Big Bang model is correct, and general relativity is correct, and the Hoyle-Narlikar new theory of gravity is not the correct theory. But at the same time, I must give homage to both Hoyle and Narlikar, because they had the courage to propound in a very creative and original manner alternate scenarios, so that the mainstream theories can be rivaled against the alternate scenario. So with this, I stop my lecture, and I'd be very happy to answer any question that is raised.
Thank you for very nice presentation, and now it's open for question. Anybody who has question, please unmute yourself and ask your question. Or you can also raise your hand, means whatever is convenient. Especially, I request students to, students, you can ask whatever comes in mind, means don't be hesitant in asking
Exactly.
question.
Because in science, you must ask question and not believe anything that is being told to you. That's the spirit of science. And that was the spirit that Hoyle and Narlikar propagated, that don't believe in mainstream theories, but make your own theories. Ultimately, observations and experiments will tell which is the correct theory. So please go ahead. As I always told my students, there are no stupid questions. All questions are legitimate.
Shobham, please unmute yourself and speak.
Yes, sir. So, what is the major difference between the steady state theory and the quasi steady state theory?
Correct. Very good question. So, in the steady state theory, the scale factor A of t increases monotonically as e raised to power ht, where h is a constant. So it is exponentially increasing. While in the quasi-state steady-state theory, the as I showed, let me again share the screen and show the picture. That I hope you can see the screen. The scale factor A of t that is oscillating about a mean value which is going as e raised to power ht, but there is an oscillation. And quasi-state steady-state model basically incorporated that the C field time to time undergoes a mini bang, so that suddenly there is expansion, and when the expansion recollapses, it will come down. So over the entire space-time geometry increasing as e raised to power ht, there is oscillation because of time-to-time creation of banks due to the creation field. So in other words, the steady-state model is a superposition of mini Big Bang, so not Big Bang, but mini bangs over the steady-state model. I hope I have answered your question.
Yes, sir. Thank you, sir.
Any other question?
Yes, sir.
Please continue, Vijay.
So I'm always puzzled about this universe expansion. Means how do we intuitively understand that the space expansion? Because is there anything outside the universe which actually is uh, explained
Very
by
good,
the?
very good question. So remember, I mentioned that the universe has matter that is distributed homogeneous and isotropically. So that means there is no boundary. And if there is a boundary, then beyond the boundary, there is no matter. Then the universe cannot be having matter that is distributed homogeneously. Homogeneity means that you go to any place, the universe, the matter distribution will look alike at a given time. Isotropy is that when you orient yourself in any direction, the universe will, on large scales, look the same. So this assumption tells us that universe cannot have a boundary. And indeed so that the universe either is infinite in volume, or in the case of a collapsing universe, the total volume is finite, but it doesn't have a boundary. So such a thing can be explained using general relativity with a suitable geometry. And to answer your question, the universe is infinite. That means when Big Bang happened, then at every spatial point, suddenly matter was created, and they are all moving away from each other. The Big Bang, unlike these pictures a little bit misleading. The Big Bang did not take place at one spatial point. Big Bang actually happened everywhere. And that's the reason why you don't have a boundary. I hope I have answered your question.
Yes, sir.
So in other words, the two-dimensional analogy would be, imagine that there is an infinite rubber sheet, infinite extent, and you have drawn dots on it, and the dots represent galaxies. And if the rubber sheet is being stretched, the distance between two dots, they'll be increasing. Okay, but there's no boundary. Or you can think of the collapsing universe where the area is finite. You can have a balloon where the area is finite, and you draw dots and inflate the balloon. The dots, the distance between them will increase, but there is no boundary. The surface of the sphere doesn't have a boundary, although the area is finite. So these are you can do mathematical analysis to talk about this. So there is no boundary. So you can't fall off. As if you go straight, go ahead, you can't suddenly see, oh my God, I have reached the edge of the universe. That doesn't happen in the Big Bang universe or in the steady state universe.
So we move to the next question of Dr. Shandip Chokar. Can you please ask the question?
Uh, Thank you, Professor Patak, and thank you, Professor Patrick, for your talk.
Most welcome.
My question is basically the origin of my interaction during my astrophysics classes in the university itself. And students talk a lot about the wormholes. So I
Correct.
just want to have your take on the possibility of the white hole, so that I can explain them that one day the theory of a wormhole is also possible, practically possible.
Right. So, wormhole, actually, Einstein and Rosenfeld, they talked about wormhole for the first time. So, what they said was that, this whole idea of matter getting collapsed to a singularity and matter simply cannot be accessed is not a very pleasing idea. So they talked about what if there's a bridge matter connecting the collapsing matter, and there's a narrow bridge through which matter escapes and goes somewhere else in the space-time, not where the thing collapsed, but they appear somewhere else. Like in this picture, if you have a two-dimensional space-time, the black hole is being formed here, collapsing, but there is a narrow tube called the wormhole connecting this region with this region. Now, is it possible in the real world to have such a wormhole? The idea is yes, you can work out using exotic matter and general relativity. You can create a wormhole if your exotic matter has a strange kind of equation of state where energy density is sufficiently negative times pressure. Normally, in our day-to-day life, you never encounter matter for which energy density or pressure is some negative quantity times energy density. We never encounter such a thing. But suppose theoretically you assume that you have such an exotic matter, then you can create such wormhole. So theoretically, general relativity and existence of such crazy matter for which energy is some negative number times pressure, it is possible to create wormhole. But in 1980s, Hoyle and not Hoyle, Kip Thorne and some others showed that even if you create a wormhole, a little disturbance and it will collapse. So your black hole can, a little disturbance and the wormhole will disappear. So that was the reason why the time machine proposed by Thorne, etc. If you have a wormhole, then you can create a time machine. That was a beautiful idea given by Thorne, because imagine that you are having a region, may not be black hole, a region connected by a wormhole to another region. And if this wormhole is moving with respect to the other hole, then a twin goes into this region. He will appear in the past because a accelerated twin, the time goes slow. That's famous twin paradox. So he will be younger and he will appear. So for him, time is gone back, and while the other twin is in the real time. So you can create time machine if you have such macroscopically large wormhole. But unfortunately, in fact, a science fiction by a science fiction called Contact, which was also made into a movie, was based on that idea. And but unfortunately, Thorne himself realized that such wormholes are very unstable. A little perturbation and will collapse into a black hole. As you know, stable solutions are very important. We all know that if you take a needle and we put the tip of the needle and you make the needle vertical, sufficiently vertical that the center of gravity and the tip is aligned with the line joining the center of the earth. So then there is no torque, right? And it should be standing just like that. But we know it's not a stable equilibrium. A little push and it will follow. So although solutions are possible, but if they are unstable, you can never see them in real life. And that is the issue with wormholes.
Thank you, sir. Thank you.
Most welcome.
Any other question?
Thank you, Professor, for such a very nice talk.
Most welcome.
So I want to know what kind of matter is this dark matter? Can you shed some light on that?
Yes, no, that's the billion-dollar question today. As you know, dark matter. Let me see whether I have a slide. Yeah, I think I should be having a slide. Yeah, dark matter has been indirectly deduced. As you know, Vera Rubin, she was trying to find out the rotation velocities of neutral hydrogen clouds very far away from very many different galaxies. Now, supposing you have a galaxy whose extent is this much. Now, you'd expect that as you go from the center, the rotational velocity, you use Kepler's law, whatever mass is enclosed, the rotation velocity, as you go further out, you're sampling more mass and the velocity will increase. But as you go out, now the mass is fixed. As you go out, the rotational velocity will fall off as square root of gm by r. You might ask, where is it coming from? Because anything that is rotating satisfies centripetal acceleration v square by r must be equal to gm by r square. If v square by r is gm by r square, then v is square root of gm by r. Once you go out, now the mass is fixed, no more mass, right? So here onwards, square root of gm by r will fall as square root of r. So you expect the rotation velocities of neutral hydrogen clouds will be decreasing, while to her surprise, what she found that the rotation velocity either flatten or in some cases they increase. That was very surprising. And then they modeled by saying, well, there is some matter that you don't see. They don't interact with light and therefore they don't see. There's a halo. And this halo, we call the halo to be made of dark matter. And that's the reason why when you're going away, there is also mass. And that's the reason why the rotation speed is either becoming flat or increasing. Okay. So therefore, the model was that there is this visible part of the galaxy, the disk of the spiral galaxy. Then there are globular clusters forming a halo. But beyond that, there is dark matter forming a halo, and the size of the dark matter halo could be anything like 100,000 light years to 3,000 or 4,000 light years. Or no, sorry, not 100,000, but yeah, 100,000. Yeah, 100,000 to 4,000 light years. And then people also found that there are clusters of galaxies, and the bending of light tells us all the mass that is causing bending, and that mass is more than the sum of the mass that you deduce from visible. You can see a distant quasar being gravitationally lensed, and you can see the lensed point quasar appears like this rings, parts of the ring. These are called Einstein ring because Einstein had predicted such gravitational lensing. So from all these, we know that there is dark matter. But what is the composition of the dark matter? Earlier, when particle physicists were talking about supersymmetric theories, they had talked about supersymmetric partners of photons called photinos that be more massive, supersymmetric partner of gravitons, more massive gravitinos. And they thought that gravitinos and photinos are good candidate for dark matter. And they had estimated their masses to be about 100 billion electron volt. And one of the prime motivation of large hadronic cloud was to detect such particles. But unfortunately, large hadronic cloud has not detected any such particle. So now there is a sort of move towards ultralight pseudoscalar dark matter particles. So axion-like pseudoscalars, now people are looking at axion-like ultralight pseudoscalar particle as the dark matter particle. And we have done some work where we have shown if ultralight pseudoscalar particles are dark matter candidates, you can use them to create the observed supermassive black holes on time scales less than billion years. Because there's a big challenge. How come you see supermassive black holes when the universe was barely billion years old? So, in a nutshell, we still don't know what is the composition of dark. It's one of the billion-dollar questions.
Thank you,
Hello.
sir.
Hello, yeah.
Hello. So may I ask a question?
Absolutely, yeah, go ahead.
Um, I have come across the inflationary theory by Ellen H. Booth. So,
Yes,
the question was the mini banks you were talking about earlier. Is it
yes.
analogous to the chaotic inflation mechanism?
Well, that's a very good question. First of all, let me mention what is this inflationary scenario. Now, you see, the Big Bang universe, it has three uh, initial value problem. The initial value problem of Big Bang universe is this, that no matter, we still don't know what kind of universe we inhabit, right? So is it closed universe or is it open universe? But whatever it is, the present measurement tells us that the present density of the universe is very close to the critical density. Critical density is the density which will make the universe having some uh, number called k equals 0, namely flat space universe. So one of the initial value question is, how is it that the density of the measured density of the universe is so close to the critical density? While we know that in the past, even if it is today, the difference is small, in the past, the difference would have been exponentially larger. Similarly, the other thing is that why is it that microwave background radiation in one direction has almost same temperature in the diametrically opposite direction, while in the Big Bang model, they should not be within each other's light cone and they should not have talked to each other. So how is that the thermal condition of the universe at 2 points which were never in thermal contact, how is it that the temperature is identical? So this is one big fine-tuning problem. And inflationary model, what they did was they said, well, the universe at one point expanded exponentially, okay, for a little while expanded exponentially, so that today's uh, universe, observable universe, is a tiny region which has got expanded. And tiny region, that region was within each other's causal contact. And that's the reason why now that that tiny region has expanded to today's observable universe, that's why the temperature is identical. Similarly, because the expansion was identical, that k value, that k in the equation comes as k divided by the scale factor square. So if a, the scale factor exponentially increases, no matter what the value of k was, whether k was 1, -1 or 0, k by a square will be so tiny that it is indistinguishable from k equal to 0 model. So inflationary model explained it very beautifully. But unfortunately, by the way, steady state model did not have these problems because steady state model always was eternal and the density was always fixed. So steady state model never had that problem. And therefore, in the quasi-steady state model, there will be fluctuations, but overall, there is a steady state expansion. So therefore, the fluctuation, even if it is not critical density, the fluctuation can be explained by this minor oscillation, but overall, there is an exponential expansion. So the quasi-steady state model doesn't require the inflationary model to solve the fine-tuning problem, namely the density flatness problem and the temperatures of microwave background being almost same in two opposite directions.
So we'll take two more questions. Means the last one is by Professor Ajay Srivastava, and then we'll move for Lavi and before we close. So Professor Ajay Srivastava, can you please unmute and ask your question?
Yeah, hello sir, good evening.
Good evening, good evening.
Sir, my question is that how the dark energy is differentiate from the dark matter, and what is the driving force behind the dark energy?
Yes, so very good question. So dark matter is some matter which is like any other matter except that it doesn't interact with light. And that's the reason why they will never be seen electromagnetically. But you can see they're present through gravitation effects. On the other hand, the dark energy, it has to cause exponential expansion. That means there is some kind of anti-gravity because the expansion is happening at an accelerated rate. Normal gravity will only cause deceleration. All these models, the scale factor is increasing, but the increase in the scale factor is associated with deceleration because gravity is attractive. Dark matter gravity is also attractive. But now that people like Rice, Smith, and Perlmutter with using one of the standard candle called supernova type 1a, they deduced that universe is not only expanding, but the expansion rate is increasing with time. That immediately created a problem that if gravity is attractive, how can it allow accelerated expansion? But the nice thing about general relativity is general relativity allows such accelerated expansion provided you have a matter whose pressure is some negative quantity times energy density, just like the matter you need for wormhole. So if you have some kind of exotic matter whose pressure is some negative number times energy density, then general relativity itself tells that there will be repulsive gravity. So dark energy is some exotic matter for which the equation of state is energy dense, is pressure, is some negative number times energy density. For example, normal matter, we know that if you take radiation, for radiation, what is the equation of state? Pressure is 1/3 energy density. So 1/3 is positive. On the other hand, for this dark energy, dark energy is a name for that exotic matter for which pressure is some negative number times energy density. There are many candidates for dark energy, things like quintessence, for which pressure is negative times energy density. Then I talked about phantom field, which is like the creation field postulated by Hoyle and worked upon on it, Hoyle and Narlikar. The phantom field is very much like creation field, where energy density itself is negative. In other words, dark energy and dark matter, although they are prefixed by dark, they are two very different kind of matter. Dark matter is normal matter except they don't interact with light. But dark energy is exotic, purely exotic. We don't have any seen object which has such property.
So Labi also raised hand. Dr. Labi, you
Thank you,
can
sir.
ask your question.
Thank you, sir, for the nice lecture. The question is regarding the steady state model that the density remains nearly constant and a little bit mass increases. So how it satisfy the mass can neither be created nor be destroyed.
Yeah, so in
Matter
steady
can.
the volume is increasing, but if you want to maintain the same density, then you have to create matter spontaneously, right? Otherwise, how can you have same density when the volume is increasing? I mean, over the observable universe, that the total mass is increasing because volume is increasing, density is constant, mass is increasing. So you have to create mass. And so you don't have any normal physics that can do it. And that's the reason why Hoyle and Narlikar proposed a bizarre field called creation field, or in short, C field, whose equation, the elevation of C field times 1/6 the Ricci scalar times creation field is related to the particles present at different points. Okay. And they source the C field, and C field in turn create matter. So that is how they explain how you can have a steady state model. But as I said, that there is no observational confirmation of steady state model, and therefore you can question the
Its impact will remain because this is recorded and it would be in YouTube. So is someone asking something?
Yeah. So today we must confess that there is no evidence for such a C field which can create spontaneously matter out of vacuum.
Okay. So before I end, means I just want Dr. Santosh Shukla, who is Executive Secretary, National Academy of Sciences, India, to say a few words. And before that, I just want to make a small correlations. Means many good things happened in 1930s, and one good thing was that 1930 Nashi was established, and the other good thing is that 1938 Professor Narlikar was born. So the journeys started in 1930, and then he became fellow at 1988, and then the interaction continued. So on behalf of NASI, I would like to request Executive Secretary Dr. Santosh Shukla to say a few words before we close.
Thank you very much, sir. Am I audible,
Yes,
sir?
you are audible.
Thank you very much, sir. And you are just for saying that in 1930 Nasi was established, and one more thing was also held that the founder of the Nasi was also a great patriotic scientist and physicist, Professor Meghnad Saha. Not only this academy, even all the three academies were founded by the physicist. That is also just a coincidence. So, on behalf of Academy headquarter, I am very much thankful to Professor P. Das Gupta sir, who has definitely delivered a very illustrative lecture and explained the very so mysterious cosmos in a simpler way, just like in Professor Narlikar's style. So, on behalf of Academy and my own, we are very much thankful to the speaker, esteemed speaker, as well as many thanks to the organizer Nasi Delhi chapter, especially Professor Ajay Ghatak sir and the convener of this program, Professor Anirban Pathak ji, who has continuously making the series of such lectures. So many thanks, and also the participants who has so actively involved in even the show. It is not 8:45 and people are here, so we can see the zeal of the participants also. So many much thanks, and hope this series will be continued, sir. On behalf of the academy, thank you very much.
Thank you, Santosh, and thank you everyone for joining. And before I close, I just want to ask Professor Ghatak, do you have any remark to make at the end? Sir, do you have any remark?
I have no remarks. I just greatly
Okay, sir.
enjoyed Professor Dasgupta's lecture, and as Santosh very rightly pointed out, I have heard Professor Narlikar only once, and I had the privilege of sharing a meeting with him and then interacted with him over 2 3 days at Pune. It was a great experience. His wisdom, his words of wisdom, his simplicity, and everything. And as Santosh mentioned very rightly, that Professor Dasgupta also is a great speaker. I mean, it's like Professor Naldikar. He has covered a huge range of topics, wide spectrum of topics, and uh, and always sort of concentrating on the
Thank you very much.
physics,
Thank you very much.
on the physics, and I hope the younger generation gets motivated to learn physics, and we continue to get good students in physics. So, so I think there has to be a revival of science subjects, and there was a there was a small news item that came out in social media that the two people saying that physics and mathematics are the two topics of future, and all good students must enter that rather than going to engineering and things like that. But with that hope, I'm sure such lectures will go a long way in stimulating the young minds. I wish there was a little greater audience, but so we must have a general lecture by Professor Dasgupta at Delhi in a college or something like that to motivate the
Sure.
younger generation. Thank you so much, Professor Dasgupta, for this great lecture. And
My
thank you,
pleasure. That
Anirban. Thank you, Anirban, for doing all the hard work, and always a great you and the support that we always get from Nasi headquarters, and now particularly from Dr. Santosh Shukla. Thank you all so much for a wonderful evening. But dinner nahi hai साथ में
Sir,
or a cup of tea. That is the part missing.
that's the difference of virtual meeting and real meeting. But
Yes.
so thank you, sir, and thank you everyone. Thank you all the participants for joining.